This video focuses on the binomial distribution. The normal distribution provides a good model for many continuous random variables. It can also be used with discrete random variables when there is a large number of possible values. Here's an example. Scores represent the number of words spelled correctly and range from 6 to 18. I've superimposed the normal distribution on the histogram so that we can see that there's not much difference between the two. The probability of getting a score between 13 and 14 is this area, the proportion of the distribution represented by these two bars. Any part of these bars that is excluded by the normal distribution indicates an underestimate of the true probability, and any area included by the normal distribution that is not a part of the original distribution indicates an overestimate. Overall, the normal distribution provides a pretty good estimate for this discrete probability distribution. Here's another example. This is the distribution of number of heads in 4 tosses of a coin. And we can see that the normal distribution consistently underestimates these probabilities. In general, the normal distribution is not a good model for discrete random variables with only a few possible values. The model that we use instead is the binomial distribution. Suppose a variable could only take on 2 potential values, yes or no, disease or no disease, and so on. This type of variable is very common in biomedical research. Let's look at dental implants. An implant will either be successful or it will fail. And because nothing lasts forever, we will call an implant a success if it survives for 5 years. We draw a random sample of 6 patients scheduled for a single posterior implant. For each of these patients, the implant will either succeed or fail. If it's a success, we'll give it a score of 1, and if it fails, we'll give it a score of 0. We'll assume that 80% of these implants are successful. We'll call this variable x, and when we collect 5-year data, x will be equal to 0 or 1 for each of these 6 patients. In order for this scenario to qualify as binomial, 3 conditions must apply. First, x can only take on 2 possible values, 1 and 0. This condition has been met. Second, the values for x must be statistically independent. Independence means that observations are not associated or related in any way. Scores are not independent when knowing one value tells us something about the other. Repeated measures taken from the same source can never be independent. Here are some examples of scores that may or may not be independent. Scores from 2 subjects in the same treatment group would be independent. Knowing one subject's heart rate should not provide any information about what another's heart rate might be. But the heart rate of the same individual taken at 2 different time points would not be statistically independent because they come from the same source. Similarly, implant outcomes from 2 different locations in the same mouth would not be statistically independent. Whenever scores are related, they are not statistically independent. Most statistical tests require observations to be statistically independent. Probability calculations depend on whether scores are independent, and statistics is based on probability. Each patient has only 1 implant, so this condition has been met. The last condition is that each x must have the same probability of being equal to 1, which in this case is 0.8. We don't know in advance whether a specific implant will succeed, but we know based on experience that 80% are successful. We are making a prediction based on this past success. This implies that the population is homogeneous, that we have eliminated subjects for whom implants may not be as successful. The 80% is based on a population of adults who are healthy and not a poor risk. Knowing that all patients meet these criteria, a clinician would be comfortable in predicting an 80% 5-year survival rate. The 3 conditions have been met, so now what? We might want to know the likelihood that all 6 implants are successful, or that at least 3 of them are. Because x is either 0 or 1, if we sum them all, we get the total number of successes. This is the variable we're interested in, y. Knowing the probability distribution for y allows us to answer these questions about probability. And y follows a binomial distribution as long as the three conditions for x have been met. The parameters of the binomial distribution are its mean and standard deviation, which are determined based on sample size and the population proportion of successes. The mean is n times p, and the standard deviation is the square root of n times p times q, where q is the proportion of failures. For the implant example, the mean is 4.8 and the standard deviation is 0.98. We would expect about 5 of the 6 implants to be successful, give or take 1. With small samples, we use a binomial distribution table to determine probabilities. With larger samples, we convert y to a proportion and use the normal distribution. To summarize the topic, a random variable is any variable for which exact values are not known until data collection. Random variables are usually dependent variables. They have distributions, and these distributions have means and standard deviations. We have looked at two major probability distributions, the normal and binomial. The normal distribution is the basis for many statistical tests, and the binomial distribution is a common model for biomedical research. When the sample size is large, the normal distribution can be used as an approximation of the binomial.